Okay, I guess we can start. So, like, I just want to refresh my memory quickly on what we were talking about last week. So basically, what I was telling you is that if you have if you have any vector space, if you have any vector space and you have like a subspace of it. So I'll draw the picture for the subspace as kind of like as a piece of paper. That's kind of like the best I can do on the iPad. Then whenever you have a vector V, whenever you have a subspace, you can find its orthogonal complement. Which again, this is not like a super accurate representation, but it's the best I can do. Like you can have like the orthogonal complement of that subspace. And well, there's some certain properties that I mentioned between the two. The first one is that their intersection is only the zero vector. So the zero vector is the only vector that belongs to both of them simultaneously. So one of the things is that their intersection is the zero vector. Because it kind of makes sense, like the zero vector is the only vector that's perpendicular or orthogonal itself. And another thing that's true about the two is that their dimensions add up to the total dimension of the vector space that they both sit in. So again, like you have to think that this is both are kind of like subspaces of a larger space. So their dimensions add up to the dimension of V, where V is the larger space. So the example we were talking about, like in class, was that you have like R2 inside R3, right? And the orthogonal complement would become like the Z-axis, right? So 2 plus 1 is 3, right? So like the dimensions, like you add up to the correct one. Another thing, I don't think I mentioned this. By the way, I'm almost done writing the problems. I just wanted to see how much I would cover today. But yeah, I'm almost there. So first, need to kind of like work on some like things. Hopefully, you'll find interesting. So the other thing that's kind of like true is kind of like a decomposition. That if you have any vector v, right? If you have any vector v, you can always kind of like break it apart or decompose it into a sum of two vectors. One vector is on W, and the other vector is on the orthogonal complement. I may have said that, but I didn't. I don't think I said like the next thing about the. So I'll call this one VW, and I'll call the other one VW perp. And it is to like you really have to think about it as being like a kind of like a you could really draw like a right triangle if you wanted to as in each picture. So there's kind of like a Pythagoras theorem that says that the length square of the vector b is the length square of the vector of the projection. That's usually how that's called, plus the length square of the complement. So you know v is like v w plus VW perp. And the nice thing is that that's a unique decomposition. Like that can be done uniquely. In fact, this is one of the problems that I'll add to the assignment. You can kind of like set it up as a Calc 3 problem of like a least squares problem. Like how do you find this this decomposition? So basically, I don't know how clear it is in this picture. But the idea is that one way to characterize this red vector is that this vector is going to be it of all the vectors that you can draw on W, that this one is kind of like in a sense the closest to the vector V. So it minimizes kind of like the like a distance function. So it's kind of like a minimum of a function. So you can set it up kind of like as finding the critical point of the function. So I'll kind of like write it down so that you work it out if you haven't seen that before, because it's a fun exercise, and also because it's like an idea that will be later useful when we talk about kind of like things that are similar to like least squares problems. So the idea is that of all the vectors on W, this is the closest vector on W to V. This vector is the closest to V inside W. So that is like a least squares problem, because you're kind of like, again, trying to minimize like a kind of like a distance squared. So and again, I'll write down the details on the as one of the problems or the assignment, so that you can kind of like see how everything looks like, because it's like a nice calculation to work out. Um, and yeah, just to finish this, like what I was saying is that the length square of V would be the length square of VW plus the length square of VW perp. So this is kind of like a Pythagoras theorem. Well, I guess like usually the length you just use like a single absolute value. So like the magnitude squared of V is the magnitude square of VW plus the magnitude square of VW per. Sorry, let's just wait on it. And kind of like the last example I was doing last time, which again I added as an assignment problem so that you can finish just working out the details, is that there is kind of like an you can apply this even when the kind of like a similar idea even when the vector spaces are not of finite dimension. So for example, you could look at all the all the functions defined on a closed interval, right? So like the example from last time, your vector space could be like all the functions defined on negative pi to pi. Like, to not get into too many technicalities, it is easier if you just say that the functions have to be continuous. Otherwise, you have to get into too much like stuff that it's not worth like going over here. But if you take like course like in real analysis, something like I do talk about it more carefully. Yeah. But it is like, if you look at all the continuous functions, like defined say like the interval negative pi to pi, that is a vector space, because the sum of two functions is a function, because you can multiply a function by a number, that's still a function. So this is kind of like a vector space. If you kind of like look at the original definition of a vector space that you learn in linear algebra, the only difference with like the linear algebra case, like from 250 that is that this has infinite dimension, meaning like there's just like if you look for a basis, you do need like infinite many vectors like to create like a basis. So that's kind of like the only like, well, it's an important difference, but like many other things kind of like work in a similar way. And then if you have like those if you have a vector space of functions, you can actually define kind of like a dot product between them, which is what I was explaining last time. It's just like an integral. So like the dot product between two functions, which again, no one writes like as a dot product, like really like the more fancy way of writing it. Well, I'll use Dirac notation. So like the more fancy way of writing it uh, is like this. And this sometimes it is called a bracket notation or like Dirac notation because like Dirac invented that for quantum mechanics. So, I mean, like, but again, like, it is for us like a more fancy way of like, saying a dot product. So the idea is that the dot product between two functions um, is just like the integral from negative pi to pi of f of x times g of x. And again, you can kind of like check that that's supposed to satisfy the properties of a dot product. It's kind of like the continuous version of like a dot product, if you think about it. And for example, and this is one of the assignment problems, is that to how to work it out. That if you look at the even functions, like the sum of two even functions is even, and if you multiply an even function by a number, that's also continues to be even. So the even functions, they are a vector subspace of the space of all functions. And for example, the orthogonal complement are the odd functions. So like meaning that an odd function is perpendicular in a sense to an even function. So the orthogonal complement in this case is like, well, I messed up the color scheme, but it doesn't matter. They would be like the odd functions. So, like, there are many cases, where this idea of like an orthogonal complement, and things like that can be applied, maybe not today, but like next time I'll tell you an example, like, for electromagnetism also where that is used. Um, but, but yeah, it's kind of like, good to kind of like know that, that you can use it in many different, ways. That's also important in doing for like Fourier analysis and other things like of that sort, or you kind of want to decompose a function into like a sum, like kind of a normal basis or something like that. Um. Oh, okay, so that was a slight detour, but just to kind of like wrap up this thing I was telling you about the equivalence classes. So the idea is that so like back to this stuff about the equivalence classes. So what we were talking about is that when you have a vector subspace, when you have a vector subspace, you can, and you have, let's say you have two vectors v1 and v2. You can say that they are related if their difference belongs to the subspace. So that's kind of like, that ends up being like an equivalence relation. But you say that v1 is related to v2, and we did check that before, so like I'm not going to go over it again. V1 is related to v2 if I'll put like the if with two f's, which just means like in mathematics, like if and only if. So that's kind of like the defining condition. V1 minus V2 belongs to W. And then again, that forms like an equivalence relation. So again, like just to go to this very concrete example of like an equivalence relation that we had discussed like with the people, right? Like, or the students, you could say that two students were related if they had the same major, right? Like that's kind of the easiest one to understand, like to keep an idea on the back of your head for what an equivalence relation is, right? So if two students are both biology majors, they're related, but if one is a biology major, the other is a math major, they're not related. Right, so the point of the reason why equivalence relations are nice is that because they break up the population into classes or into partitions it. So in the case of the students, it was just like they're being distinguished by their majors, right? So now the total population is break into subpopulations, and no member of a population can belong to both of them. Okay. Um, so in this case, you can ask for like the equivalence, the quotient space. Let's just say this. When you say the quotient of two vector spaces, which kind of like sounds weird, you know. Because it kind of like you would read this as like E divided by W, right? And it's kind of like weird. What does it mean to divide two vector spaces, right? I mean, you can divide numbers, right? But what does it mean to divide two vector spaces? So that is just a name that's given to like the equivalence classes of this relation. So this just represents. So this is called like the quotient space. And that's just like, yeah, again, like it's really just like a fancy name for referring to the equivalence classes like of the previous relation. So it's just like a name refers to the consists of the equivalence classes of the previous relation. But again, the point is that in this case, you can be a little bit more concrete because in this situation, you do have like a very good understanding of what the equivalence classes are. So you don't have to work in such an abstract way. It is possible to do that, but that's not what we're going to do, just to be more concrete. But if you take like algebra courses like group theory and topology, I mean, well, topology is not like an algebra course, but many different areas in mathematics have kind of like an idea of like a quotient. So you can take like the quotient of groups, or you can take the quotient of a topological space and things like that. So, but in the case of linear algebra, it is super concrete to describe this because of the orthogonal complement. So that's kind of like the nice thing. So there's a very concrete way to think about this. About the quotient vector, the quotient space. And again, what is the picture? It's just like the orthogonal decomposition, because if you have, let me see if I do it here. Here's like the way to think about it. If you have a vector v1, right? Because of what we were talking about, you can write this as, you can break it into two pieces, right? I'll just use red for like this one. You can write v1 as Oh, let me call them U and V actually, so that I don't have to use too many subscripts. So if this is a vector V, you can break it into like the shadow it makes on the subspace W, which was like what I was calling before VW, and it has like this complement, which is called VW perp. Okay, and if you had a vector U, you can kind of like do exactly the same thing. If you had a vector U, you can also decompose this vector U into two pieces, right? So you have like you have its complement, sorry, UW, and then UW perp, okay? And so again, what's the condition for them to be related? They are related, provided that their difference belongs to W, right? So the idea is that U and V are related. U is related to V, provided U minus V is in W. But what is that? What is U? U, again, it's the sum of these two vectors, so it's UW plus UW perp. And V is VW plus VW perp. Okay. So this difference is really UW minus VW plus UW perp minus VW perp, right? So this difference is this is just UW minus VW plus UW perp minus VW perp. Okay, so these two vectors, like the ones in the first parenthesis, are both in the vector subspace W, which is kind of what you see in the picture. So just from the fact that W is a subspace, automatically this is already inside W for free. This is in W for free because, like, again, W is a subspace, and whenever you have a subspace, if you add vectors or subtract vectors, they're still in the vector subspace. So this is automatically in W. Okay. And the orthogonal complement is also a subspace, right? So this is automatically in W paired, right? This is automatically in W paired in the orthogonal complement. Right, so if you want the difference to be just in W, that forces this one to become zero. For them to be related, again, the condition for the vectors to be related is for their difference to be in W. So you can only have this factor. So this has to be the zero vector. Okay, so to get something in W, you need this to be zero. So we need this to be zero. Okay, so kind of what you find out from this, from this picture is that to basically another way of saying what this equivalence relation does is to say that two vectors are related if kind of like the heights, if you think of you can think of these two vectors are as kind of like the shadow of the vectors on the vector subspace. And so this is kind of like a height in a sense. So like the idea is that two equivalence relations are two vectors are related under this equivalence relation if they have the same height with respect to the vector subspace W, which is what we had done before, if you remember, with R2 and R3, because if you had R2 and you had like the vectors in the two vectors in R3, right? If you think about this as W, what we had said before is that they were related. You know, in this case, like it is the same, but here you needed that Z1 minus Z2 had to be 0. So that meant that they had the same value for the Z coordinate. Okay. So which is kind of their kind. So let me just write this down. So what we found, so this means U and V are related, is related to V, provided UW perp is the same as VW perp. So this means that they have the kind of like the same height. So the idea is that any vector, so basically what that means is that any vector in the orthogonal complement would give you a different equivalence class. So any vector. So any vector in the orthogonal complement gives a different equivalence class. And that is really like the best way to think about this quotient. So like the equivalence classes, they basically you can think of them as just like the orthogonal complement. So you can think, so kind of like the punchline or like like the takeaway of this. So and again, this is kind of like the most concrete way to think about this is that the quotient vector space, this quotient vector space is just the same. Well, I mean, I should just to be a little bit more correct, can be thought of or can be regarded as the complement, the orthogonal complement. And that is actually what we're going to do in this course, because maybe I should say how this is related to like, why am I doing this? So the idea is that, if you have like a space and you kind of want to measure like what are some of like the qualitative features of the space, like for example, if it has holes or not, then you have to create some vector spaces, and the dimensions of those vector spaces give you the number of holes. Like those are called Betti numbers. But the idea is that these vector spaces are quotient spaces, but because the quotient spaces are just orthogonal complements, for us, you can just find them. You just have to compute like the orthogonal complement to a vector space. So each would be actually, I'll do like maybe not on Thursday, but definitely by Tuesday. I think we should have enough to kind of like do a concrete case with the graphs. Um, where like, how can you tell if a graph is connected, or, how many closed loops there are in a graph. You can set that up as a linear algebra problem, and then you can define something called like the graph Laplacian, which is like a very useful matrix to have that gives you information about the graph. Um, uh, So that is also almost going to be like a wonderful application of this type of things. Um, like two graphs and all these things which are like more concrete things to work. Um, and another thing that this tells you automatically is that this this tells you the dimension of this vector space, because the dimension of this vector space will just be the same as the dimension of the complement, the orthogonal complement, but that's just the dimension of D minus the dimension of W. So that's another thing that's nice here. But again, we will always be working with the orthogonal complement. That's kind of what I'm trying to say. Uh, this is total, okay, this is, uh, do not get into too many complications, like, if the vector space is at finite dimensional, which is definitely what we will work with, most of the time in this class. Then, this is 100% always the case. The only thing that is, okay, subtle is that, to talk about the orthogonal complement, you do need to have like a dot product in place, like an inner, like sometimes that's called like an inner product as well. So this is, okay, so in mathematical jargon, this is what a mathematician would say is not canonical, because to make this identification, you needed an inner product. So you need an extra data on the vector space. So it's not something that's, but the thing is like when you work on Arc and kind of the standard inner product is the one that everyone can think about. So, but in general, but it is always like true that if you have a dot product in mind, you can always do this, like, but again, kind of like this is kind of like the most abstract way to think about it. But if you have like kind of like a dot product or an inner product in mind, then you can kind of always regard it in this way. And that is without any issues. If you're working kind of like again, with finite dimensional vector space, there's something that can happen. Which I don't know like how much we'll get into this. Like the thing is that you can do vectors, you can work with vector spaces where the scalars are not real numbers. Like for example, you can you can work with complex vector spaces, which is maybe something you have heard of. But you can also work with vector spaces with the scalars. Like for example, the scalars are just 0, 1. Like for example, like Boolean numbers, like 0, 1. Those are called like finite fields, like So in that case, you definitely have to be different. That's definitely not the case in those cases. Like the characteristic of the field has to be 0 if that means anything to you. Like you cannot have like, if you have something like, I don't know if you remember when I talked about arithmetic mod 7, like in arithmetic mod 7, you can get to 1 plus 1 plus 1 plus 1 plus 1 plus 1 plus 1, 7 times equals 0, right? And that's called like the, like the character, you would say that that's characteristic 7 because it does, if you always like add a number with itself 7 times, you get 0. But with real numbers, that never happens, right? If you add 1 to itself infinitely many times, you never get back to 0. So, like the real numbers are called characteristic 0 fields. But you can do linear algebra over fields, which is not characteristic 0. So that you could have like a matrix where like all the entries are Boolean numbers, or like, something with arithmetic mod 5 or mod 7. And in that case, like this is not true. And then you do have to think about it in this, like, with equivalence classes, you cannot just pass to the orthogonal complement. But we're kind of doing it very down to earth. So this will always be true for our examples, but you can definitely go this in situations which are a little bit more like complicated. what's going on, but not, but for what I'm saying, like on R, like, like the standard finite dimensional vector spaces that where the scalars are real numbers, this is 100% true, there's no, there are no issues with what I'm saying. Um, so, right, so let me just kind of like lay the groundwork for how this is going to be used next time. So the idea is that if you have, when you have like two vector spaces, right? If you have two vector spaces, the interest in linear algebra, the interesting functions between two vector spaces are like matrices or linear transformations. Like depends on how concrete you want to be, right? But like again, if you want to think about it at the most concrete level, just to make our lives easier, right? If you have a matrix, as we said, like if it's m by n, right? Like again, what that means is that you eat a vector of. Okay, now I'm just going to make sure that I'm using the correct term and indices for what I'm going to tell you about next time. Ah, here you are. Yeah, okay, this is fine. So again, if you have a matrix which is size m by n, right, what that means is that n rows and columns, so you can multiply this matrix by a vector with n entries, right? So as a function or no, as a function, it starts on Rn and it ends on Rm. Right, and again, the idea is that it takes a vector v and it produces a vector a times v, right? So that is what the matrix A does, right? So that's kind of like how you think of a matrix as a linear transformation. And as we talked about last time, when you have a matrix, there are two important vector subspaces that the matrix define. One is the nullity of the matrix, right? Or the null space, sorry, the null space. So one is a null space of the matrix. And the other is, the null space is just like the vectors that solve, right? Like the vectors that solve a times v equals 0. And the other important vector space that the matrix defines, sometimes it's called, like, as I told you last time, it's either called a range, or you can think about it as a column space. But maybe I'll call it the image of the matrix. Let me put this here. The other important vector space that it defines is called the image of A, which again, this is called the column space. Oh, actually, this is where like A times V lands. So maybe I should draw this so that it includes like A times V in my picture. So let me take this back. Yeah. In the column space, which again, like that literally means like the vectors on our end, the vectors on our end, which can be written as the matrix A times a vector V from R. Okay, so that is a situation when you have a matrix, okay? What you want to do in the context of this course is actually, we don't work just with a single matrix, we will actually work with a chain or a sequence of matrices. So after one, it comes two, so the next step is just when you have two matrices. Okay, so we're going to have two matrices. So for our purposes, we want to study with two matrices. So I'm going to call the first matrix A again, which is m by n, and I'm going to call my second matrix B, and B, I'm going to call it, I'm just checking my notes to see what sizes I'm using. Okay, it's going to be n times, well, let's say L. Let's do, maybe L is a better letter for this. Okay. But the thing is that the matrices are not going to be independent of one another. They are going to be connected, and the condition to connect them is that their product gives you the zero matrix. Okay, so the product of the two has to be the zero matrix. So in which order can you take this product? You can do A times V, right? These, right, because if you look at the sizes, this is n by n, this is n by l, so these two numbers match, and that's when you can multiply two matrices, right? So the condition is that this is going to be the zero matrix of which size? Well, in this case, the zero matrix would be size n by l, right? So this is like the key condition that we will have. And you'll see this like in a moment. I'm actually going to give you some examples from multivariable calculus after I write all of this down. Because it's like an important action fact. Like motivation for like a lot of the things we're doing right now. But the key condition is that they're not two arbitrary matrices, or like let me say it another way. They can be whichever matrices you want in the world, as long as that when you multiply them, you get the zero matrix. That's the only requirement that we are putting on them. Okay, and the thing is that it's nice to kind of like draw what's going on here. So because B, right, what's happening in this picture? So now we're really working with three vector spaces because B, what is happening with B? It is a size n by L matrix, right? So again, like this means that the B goes from RL into Rn. Actually, this is the one that I need to be the largest one. So maybe let me see if I can redraw this a little bit. So again, B goes from RL into Rn. And then A, well, I should use a neutral comment. A goes from Rn into Rm. So A, so let's put this in red actually. Okay. So if you kind of again, is this picture making sense? Like enter like size wise? No. So it is again like you have to think about it kind of like as a sequence of matrices. Yeah. Now remember each matrix has two vector subspaces, which is like their null space and their column space, right? So again, like in the green one, that's where the null space of B lives, right? So the null space of B lives here. The column space of B lives here. And for the matrix A, the null space of A lives in the middle, and the column space of A lives lives in the third one. Okay. And what's happening is that I'm drawing the picture in the middle on purpose as being misleading. Right now it's misleading because I haven't used this information. So if you have just two random matrices, right, you can draw their null spaces and column spaces, and you don't expect them to be too related at all. But the fact that A times B gives you the zero matrix, and I'm about to prove it because it's like a 2-minute proof, like 2-second proof actually, it's a one-liner. The fact that this happens means that the column space is completely inside the null space. So the column space will live inside the null space of the matrix because of like this magic condition. So my picture is actually misleading, so I'll kind of do the correct picture. So let me erase this and kind of draw the thing that is actually correct. So what's really true, maybe let me make it a little bit larger, is that if you have, again, like here, you would have the column space of B. And the idea is that it lives inside the null space of A. Because of this key condition. So this is my claim. My claim is that because A times B equals 0, the column space of B in general is a subspace of the null space of A. So here's my claim. Sorry, I'll just copy paste the picture and put it on the next slide so that we can kind of still look at it. So here's my claim. Since A times B equals 0, the column space of B is a subspace of the null space of A. Before I prove that, like, why is that important? Because if you just look at what's happening, then you have a vector subspace inside of a larger space. So you can then you could do the quotient, like the null space divided by the column space, and or like the image, like again, you can call the column space an image. And whenever you have a null space divided by an image, that's what in topology is called like a homology group. So this is where like the homology, which is kind of like the most important thing in topology, like or algebraic topology. So what this is going to allow us to do is that we'll have, again, this is called the image of B. So because of this, we will be able to consider the quotient space. Which quotient of the null space I mean, you kind of like think of it as being divided in a sense by the smaller subspace. And that's what in algebraic topology, algebraic topology is like just the name for like the part of topology that uses algebra to study space. Like it's called like a homology, a homology group. But again, like that terminology, like you don't have to worry about it. Like it's like a very like from our perspective, it will be a very concrete thing, and this will. But yeah, in algebraic topology, this is called like a homology group. But again, for now, we don't have to worry too much about that. What I'm going to do is kind of just explain why is a column space a subspace of the null space. And also give you some more concrete examples so that you see this is not like actually like an arbitrary situation. It's actually one that you already know because that already happens in Calc 3. So I'll show you where it happens in Calculus 3. Okay, so let me just like let me explain why the claim that y is so y is a column space a subspace of the null space. Okay. So let me just copy paste this picture and go to the next slide. Oh, actually I can fit it here. But so okay, so why is this true? So again, you start with the vector W. Let's say that you have, what does it mean for something to be a subspace? I mean, they're already vector space. What you have to check is that one is contained inside the other. So what you have to check is that if you have a vector in the column space of B, then it is in the null space of A. So so what you want to check is that if you have a vector W, so want to check that if W is in the column space, then W is in the null space of A, right? But what does it mean to say that W is in the column space of B? Almost by definition, that means that you can write it as B times a vector. That's what it means to be in the column space. That is B times a vector. So because W is in the column space, okay, this means this is the same as saying that that W is B times V for some vector V, okay? For some vector V. Well, and then what is A times W? What is A times W? Let's just work it out. A times W, in this case, then just becomes A times V. But you know, like the parentheses don't really make a difference here because like the matrix product is associative in the sense that you don't need to put like the parentheses. So it's, or like you can move them around. So that's the same as A times V. A, I should have used different letters, but. Oh, but what is A times B? Oh, that's a zero matrix. And the zero matrix times anything is just zero. Perfect. Okay, and that's what it means to be in the null space of A, right? Because A times W is zero, so you know that means that it's in the null space.
Can you explain why all the quotient, like why is it a quotient space?
No. I meant like no. Once it's not that it's a quotient space. It's more like you can take their quotient whenever you have a vector space inside another one, right? Like the idea, right? Like neither of these is a quotient space, right? What I was saying, like just to go back at the beginning, like the setup was like, oh, you have a vector subspace W, right? That lives inside a larger vector space V. Once you have that situation, you can introduce this equivalence relation, right? Where do you have it? Like I think I have it. Yeah. Once you have a vector subspace of another one, you can introduce the equivalence relation. But that does require one to live inside a larger one. So what I'm saying here is that once you know, right? If you wanted to, like once you know that the column space lives inside the null space, you can introduce an equivalence relation where you say two vectors in the null space are related if their difference belongs to the column space of V. In fact, maybe I should write it down explicitly so that like because that's where we're headed. So once you know this, you can say that like then you can do like an equivalence relation on the null space, which is like which is just that two vectors, W1 is related to W2 if W1 minus W2 belongs to the column space of the matrix B. And here, W1 and W2 belong to the null space of A. So maybe just to make the picture a little bit larger, like, again, you have the null space of A. Here's where you have W1 and W2. And here you have the column space of B. So what you're saying is that they are related. They are related if they are related, there are differences inside the column space. But that's essentially this quotient thing that I was saying, that is essentially what the equivalence classes of the relation is called by definition like the quotient of the vector spaces. Right, so that's kind of like what's happening.
So the quotient space is always when you define your equivalence, that's this like.
Yeah, exactly. It's always in linear algebra, it's always given by this condition, that quotient. Yeah. But and this is what I will do next time, because of what I was saying, this quotient space, you can just think about it as kind of like your orthogonal complement of the denominator, like the one that appears in the denominator. So but what we have to do is kind of like look at the orthogonal complement of B, of the column space of B, but just like the part that lives inside the null space, because we're just kind of like ignoring everything else. But again, I don't want to get into those things today because it's a little bit more technical. Maybe just to kind of like show you that this is actually more concrete than you think. Like, let me give you like a Calc3 example. Here's like a Calc3 example. I put more of these details on the assignment, but it's just kind of like explain actually some of it, so that you see what's going on happening here. So if you have a function, right, a function in Calc3, like a function that depends on X, Y, and Z, right? Hopefully someone remembers this, right? What is a nice way, if you have a function, as a scalar function, in Calc3, how can you produce a vector out of it? How can you create a vector out of a function? You can take their gradient, right? Like you can do the gradient of the vector, the gradient of the function, right? So and the gradient was like an important vector. It's not just like any random, it's a vector field, right? Because it's not just like a single vector, it's like a bunch of like vectors, right? So the gradient of f was, which also like you can write it as grad of f. The other notation is nabla f. So if you remember, or if not, I'll kind of like write down the formula again. You take the partial derivative with respect to x, the partial derivative with respect to y, and the partial derivative with respect to z. The partial derivative was equal to z. So the gradient was just like the three partial derivatives that you could take, kind of like arrange as a vector, right? Like the first, if you don't want to write it in terms of I, j, and k, and just like in terms of like the entries, right? Like the gradient was the partial derivative with respect to x, followed by the partial derivative with respect to y, followed by the partial derivative with respect to z, right? Now, and then the gradient, right? If you think about it, the gradient is linear in the sense that the gradient, right? Actually, I'm using the correct color because I will follow the same color scheme. The gradient of the sum of two functions, right, is the gradient of f plus the gradient of g, right? And if you multiply a function by a scalar, right, like by a constant, I mean, you can take out the constant out of the gradient. That's just because those are the properties of a partial derivative, right? Like a partial derivative of a sum is the sum of partial derivatives. And the partial derivative of a constant times a function is just that constant times the partial derivative of a function. So it's kind of like the gradient inherits those properties from the partial derivatives, but these are like the defining properties of what you call like something being a linear function or a linear transformation. So this is called linearity for a reason, because literally that means that you can regard the gradient as kind of like a linear transformation, kind of like as a matrix that takes in functions and outputs vector fields. So one way to think about it here is that kind of like to do my diagrams. Here is where like all the world of functions live. So functions on R3. So here you have a function f, and then the gradient, what the gradient does is kind of like produces a vector field, right? So this is where like a gradient, you take, it kind of looks like a weird notation, but you could call it grad if you want. But and then that produces like the gradient of it. Okay. So from that perspective, like the gradient is kind of like a matrix. It's just like because the vector spaces are infinite dimensional, it is kind of like an infinite dimensional matrix. Like, you can kind of like actually represent it by a matrix if you wanted to. It's just because instead of having like infinite rows and infinite columns. It's kind of like just easier just to think about it as like more abstract thing, as a kind of like linear transformation. Now, here, so I want you to think of the gradient in analogy with what I'm doing. The gradient is kind of like a proxy for this matrix that I call P. Like, we have these two matrices A and P, and the gradient is kind of playing the role of P. So think of gradient of the nabla thing as a matrix B. So think of this one as B. That's why I'm using the green color, because I think that's the same color that I had for B. So think of this as B. As the matrix B from before. And then, okay, so here's another thing from Calc 3, like almost like maybe like last week or so, last 2 weeks on the course. If you have a vector field, which if you want, you can think of it as a force field, if it makes helps your imagination. If you have like a vector field, okay, what was like a useful operation that produces a new vector field out of it? How can you create a new vector field out of like a starting vector field? And it's was one of the important ones from like the end of Calc 3. Which operation appearing in Stokes here with like kind of like those like I think.
Yes.
Well, good. It's not going to be the divergence because the divergence actually produces a scalar, but the divergence actually plays a role, but not right now. The curl, good. So if you have a vector field, you could define its curl. Okay. Okay, yeah. So if you had a vector field, I'm calling uppercase F because if you want to think of it as force, okay? So F, not the notation I would use all the time, but if you want to do kind of like a physics interpretation, you can think of it as F1I plus F2J. I'm not going to write like the explicit formula for the curl. I'm just going to, again, I'm just trying to refresh your memory, because one goes so quickly over all this stuff at the end of the course, that it's easy to, forget what was happening there. But, like the curl had like this very funny looking formula where it's kind of like, you could even write it in terms of a determinant if you wanted. It's kind of like a weird combination of partial derivatives of the vector field. So it's kind of like take the partial derivatives of the vector field in a somewhat odd way. Okay. But my point is that the point is that what I want you to kind of like think about this in this situation is just that the curl, right? The curl of a vector is a new vector field. Okay, so the curl. So again, like the idea is that this is a new vector field. Okay, so these, what does it mean? So that means that if you have the space of vector fields, right? If here you have a vector field F, you can take its curl and you get a new vector field. Okay. And I want you to think of the curl as kind of like the matrix A in this picture. So this is kind of, the curl is playing the role of the matrix A. So here, like the curl is like the matrix A. Is that okay? Okay, and then I don't know if you see where I'm headed with this. So you could start, let's just put the diagrams together, you know. So you could start with a function, right? You could start with a function. You could start with a function f. You could take its gradient, right? You could take its gradient. Let's just write this as gradient of f, right? And then you could, because the gradient is a vector field, you could take the curl, of the gradient, right? Okay, let me see if I can move this a little bit. Just so that, okay. And then you can take the curl. This is going to be another vector field. So you're taking the curl of the gradient, okay? So this is the analog of like A times B. I want you to think of that as a A times B. So that is actually, by the way, I'm sure like you don't have time to go, like rarely does one have time to go over all these details in multivariable because like the part is so fast. But one of the most important like vector calculus identities is like the identity for what is the curl of a gradient. And what I mean, but just based on what I have been saying, like if you think of that should become like A times V. That's like, so what should like what should the curl of the gradient be? It's just zero, right? It always identically always gives you the zero vector. That's one of the most important. It's very easy to check, it's just like a brute that you can do like as a brute force calculation. But the curl, the curl of the gradient, so the curl of a gradient is always the zero. It's similar to like, the situation that we had before. So kind of what that suggests, right? What that suggests, or what that means is that, I'm almost done, but like, just kind of like to tell you how this connects to interesting things. What that tells you is that if you have the null space of the curl, right, then the column space of the gradient lives inside of it, or the image of the gradient, or like, again, that's kind of like the column space of the gradient. Okay. Now, what's kind of like interesting, and this is, this is like an important like fact, is that on R3, kind of like the nice thing is that actually they coincide. So on R3, these two, it's not that one is smaller than the other. On R3, they have the same size. I mean, they're infinite dimensional, so that just means like it does fill up everything. So on R3, the null space of the curl is the same as the image of the gradient. So what does that mean concretely? What that means concretely is that the moment that a vector has zero curl, it is the gradient of something. Okay, and so the moment. So what that means is that the moment. So whenever the curl of f is a zero vector, you can express that vector as the gradient of a function. You can write f as the gradient of a function. But what, okay, when, maybe this rings a bell. When did you check, why would you check if the vector had zero curl? What happened, what was the name for the vectors whose curl was zero?
Conservative vector fields.
Right.
Potential.
Exactly, so that is essentially saying that, that's why if you're trying to find out if a vector field is conservative, you would check for its curl because of this relation. So what this is saying is that, right, like vector fields with zero curl are like, they have a, well, usually in physics, you call like minus f the potential, like, there's kind of like they use the difference, like an opposite sign, but right, like, that's why you would just call like a vector whose curl was zero conservative. So that's why that's what's like a conservative vector. And well, yeah, strictly speaking, negative f is what like the physicists would call the potential function. Yeah, that's kind of like one of the reasons why looking for the curl to vanish was like an interesting thing to do in multivariable calculus. What happens, I mean, maybe I'll like tell you more about this like next time. But what happens is like if you're not on R3, this is not necessarily true in the sense that this can be strictly smaller than the other one. So you can have vector fields who have zero curl, but don't have like a potential function. And that's important, you know, it actually has to do with whether the space has holes or not. So it's like related to like the topology of the space. There's a similar story, which again, I wrote on the assignment. There's a similar story with the curl and the divergence. So they count like the divergence of a curl is also zero. In that case, like that means that if the vector has zero divergence, it is the curl of a vector. The vector is called the vector potential. And that's usually magnetism. Like, for example, a magnetic field has zero divergence. That's one of Maxwell's equations. And then it has like a vector potential. There's like a very fun argument by Dirac for magnetic monopoles, I don't, like it's like a little bit more advanced, but he kind of like proves that like, how was like the argument, like that if you had like a single magnetic monopole, like the electric charge would be quantized, like in the entire universe. It's called like the Dirac string. But it's a clever construction. I mean, if it's kind of like I'll think about how if it's doable to kind of like put as an exercise to work out, because it's like a very fun argument. Like magnetic monopoles haven't been found, by the way, but yeah, it's still kind of like fun to have like it involves like a wave function, so it does involve a little bit of quantum mechanics, but it's kind of like a. But the point is like all these properties of electricity and magnetism are actually related to the what you would call like the topology of the space. So if the space has holes, if you have like a space with holes, or a vector field with singularities, then like you know, you may have like a strict inclusion. So like it may not be true that every vector field your curl is concerned, like has a potential function and things like that. So all those things are important, like to understand, the Mills theories and gauge theories and other more complicated aspects of like the world. But let's finish here. So next time on Thursday, I'll tell you more like, we'll go back to the matrix case, which is the one we'll be dealing with the most of the time, but it's kind of like useful to see that there's actually this like infinite dimensional analogs that you already knew, but like you were not not being presented in this way. So, you work around.